This is to present our work about efficient frequency domain-based transformers for high-quality image deblurring. Image deblurring is a process of restoring sharp images from blurred ones. In this work, we present an effective and efficient method that explores the properties of transformers in the frequency domain for high-quality image deblurring. The main contributions are summarized as follows. Firstly, we develop an efficient frequency domain-based self-attention solver to estimate the scale product attention for effective and efficient image deblurring. Then we propose an effective discriminative frequency domain-based FFN to discriminatively determine which low and high frequency information should be preserved for latent call. Our image restoration. Finally, we develop an asymmetric network architecture based on an encoder and decoder network where the frequency domain-based self-attention solver is only used in the decoder module. Recently, several transformer-based methods have shown excellent performance in image deblurring. However, the computation of the scale product attention in transformers leads to quadratic space and time complexity in terms of the number of tokens. It is not affordable if the image resolution and the number of the extracted patches are large. We note that each element of the matrix product of Q in the transpose of V is obtained by inner product. Therefore, a natural question is that can we efficiently estimate the attention map by an element-wise product operation in a frequency domain instead of computing the matrix X multiplication of the matrix product of Q and the transpose of V in the spatial domain. To this end, we develop an effective frequency domain-based self-attention solver. Specifically, we first obtain FQ, FK, and FV by a 1-by-1 point-wise convolution and 3-by-3 depth-wise convolution. Then, we apply the fast Fourier transform to the estimated features FQ and FK and estimate the correlation of FQ and FK in the frequency domain by Formula 4. Then, we estimate the aggregated feature by Formula 5. Finally, we generate the output feature of SAS by Formula 6. We further examine the space and time complexity of the SAS and the window-based strategy for transformers. The proposed FAS is used to reduce the computational cost. As shown in the figure, using the proposed FAS needs a small GPU memory and is much more efficient compared to the window-based strategy. In addition, as the memory of the FSAS is independent of window size, the memory usage of the FSAS does not increase when the window size becomes larger. We evaluate the effectiveness of the proposed FAS. The method that computes the scale product attention in the spatial domain does not generate good deblurred results, where its PSNR value is 0.27 lower. Computing the scale product attention using the FSAS in the frequency domain generates a clearer image. As not all the low-frequency information and high-frequency information help latent clear image restoration, we develop a DFFN that can adaptively determine which frequency information should be preserved. However, how to effectively determine which frequency information is important? Motivated by the Chegg compression algorithm, we introduce a learnable quantization matrix W, and learn it by an inverse method of Chegg compression to determine which frequency information should be preserved. To demonstrate its effectiveness on image deblurring, we compare the proposed method only using the DFFN, and the proposed method only using the original FFN. Using the proposed DFFN generates better results, where the PSNR value is 0.36 decibels higher and the windows are recovered well. We embed the proposed FAS and DFFN into a network based on an encoder and decoder architecture. We note that the features extracted by encoder module are shallow ones, which usually contain blur effects compared to the deep features from the decoder module. However, the blur alley changes similarity of two similar patches from clear features. We thus embed it into the decoder module, which leads to an asymmetric encoder-decoder network for better image deblurring. To examine the effect of this network design, we compare the network that puts the FSAs into both the encoder and decoder modules. Using the FSAS in the decoder module generates better results, where the PSNR value is at least 0.17 decibels higher. Comparisons of the proposed method and state-of-the-art ones on the GPRO dataset in terms of accuracy, floating point operations, and network parameters. The circle size indicates the number of the network parameter. We first evaluate our method on the commonly used GPRO dataset. The table shows the quantitative evaluation results. Our method generates the results with the highest PSNR and SIM values. Compared to the state-of-the-art CNN-based methods, NAFNet, the PSNR gain of our method is at least 0.5 decibels higher than NAFNet, while the number of the proposed model parameters is a quarter of the NAFNet. In addition, compared to the transformer-based methods, our method has fewer model parameters while the performance is better. This page shows an example of visual comparison on GoPro dataset. The proposed method generates a clearer image. For example, the characters and boundaries are much clearer. We further evaluate our method on the RealBlur dataset and follow the protocols of this dataset for fair comparisons. The proposed method generates the results with higher PSNR and SIM values. This page shows an example of visual comparison on RealBlur dataset. The proposed method generates an image with much clearer characters and structural details. We then evaluate our method on the HIDE dataset, which mainly contains humans. The table shows that the quality of the deblurred images generated by the proposed method is better than the evaluated methods, suggesting that our method has a better generalization ability, as models are not trained on this dataset. We show some visual comparisons. We note that the evaluated methods do not recover the humans well. In contrast, our method generates better images. We have released codes and pre-trained models if you would like to try them. Thanks for listening.